Good afternoon, my calculus friends. Our virtual lectures are going to start with Chapter 4, Applications of Differentiation. Some of these notes are quite lengthy, so to save on some time, I will be just presenting some pictures and pointing at things, and you can pause and copy other things I will be writing down as we go through them. So that being said, let's begin. 4.1 in your Stewart book is equivalent to, or pretty close to 4.3 in XYZ. Now keep in mind, XYZ is created by a different publisher, so things may not line up exactly if there's something you come across in the homework. So 4.3 homework should correspond with most of the topics in 4.1. You may come across something that doesn't exactly fit in there, but eventually we will cover the material that you need to answer those questions. So anytime, please email me, come to the virtual office hours, and we will figure this out and get through it together. Okay, max and min's value, so applications of differentiation. At this point, you should all be awesome derivative takers. If you go into your XYZ homework, you will see that you have lots of problems in Chapter 3 due at the end of the semester, but you should be working on them to practice on your differentiation. So from this point forward, I'm going to assume you're good at taking derivatives, and now we're going to learn how we can use them. When we look at a function, in this case, this is a function, a continuous function defined in a closed interval. It's only defined between the values a and b. What we're interested in, it doesn't necessarily have to be on a closed interval. This example is, we will look at both scenarios, on a closed interval and then infinite intervals. In this particular case, this function is defined on a closed interval. What I want you to focus on are these things right here, the tops of hills, the bottoms of valleys, how high the function goes, its largest output appears here, and its smallest or lowest output appears here. So we have 1, 2, 3, 4, 5. It looks like we have 5 points of interest. Now, if it's up top of a hill, we call it a local or a relative maximum. So those words are used interchangeably, so relative or local maximum. So we have 2 relative or local maximums. If it's the bottom of a hill or the bottom of a valley, they're called relative or local minimums. If it's the highest the function goes, it's called a global or an absolute maximum. If it's the lowest a function goes, it's called the global or the absolute minimum. Notice here that this local minimum also happens to be a global minimum. It's as low as it goes. This absolute maximum, though, is not the top of a hill, even though it does seem to stop there. Because we don't know what goes on beyond this point, endpoints are never classified as relative or local maxes or mins, but they can be global maxes or mins. So the formal definition of these guys is, ready for all this? Feel free to copy this down if you want to have them completely in your notebook. Otherwise, you can just read through it and see if you can kind of grasp what it's telling us here. A function has an absolute maximum value of f of c for some point c, and we'll talk about the difference between these two in a minute, if the output at c is greater than or equal to all outputs for all the domains in the functions. So if we look here, the highest output occurs at this point b. So we would say that this function has an absolute maximum. It occurs at the value b, and then whatever this output is, that would be the value of the absolute maximum. A function has an absolute minimum. Likewise, just reverse the inequality. At some point d, if the output at d is less than all the other outputs for the values in the domain. So we go back to this guy. This would be d in this case. So every output, we look at this would be the function evaluated at d. Every output, every other output falls above d. So f of d would be our absolute minimum, and the absolute minimum occurs at d. A local maximum is different than an absolute maximum, because a local maximum can just happen in a small area about a point. So a local maximum happens at, let's say, a point A, if the function values all fall below f of a, just near that point. So near is a sort of a little bit of a vague term in math. So for example, right here, ignore that A for now, right here we have what we classified as a local maximum. If I squeeze in and I ignore enough of the graph, so I go a little bit to the left and the right at this point, it's the highest the function goes. So we call that local maximum because it occurs as a maximum value just locally. And I go around here, and again, right around this point, if I just look to the right and the left of this point a little bit, it's the highest the function goes in that little region. Sometimes we call them neighborhoods in math. So we would have another local maximum right here at this point. Likewise, we'd have a local minimum if we can go to the right or the left of some point, and it's the lowest point. So here we have a local minimum. We also had a local minimum over here too. So anytime it's the bottom of a valley, it's a local minimum, or the top of a hill, it's a local maximum. Local meaning local just, or that definition applies just to that little area right there. So again, here's our formal definitions. Whoops, let me slide that up so you can see them. And feel free to pause it and copy these down into your notebook. All right, moving on. Local maxes and minimums do not occur at the endpoints of intervals. So we would never, even though if this went, we would never call this a local minimum or that a local maximum. Local maxes and mins have to have something going on both sides of them. Absolute max and mins may happen at endpoints. So here we have an absolute max, which occurs at the endpoint. Here we have an absolute min, which occurs in the interval. So absolute maxes and absolute mins can happen anywhere in between the interval of definition or may happen at an endpoint. Local maxes and mins can only happen within the interval. They are not occurring at the endpoints. All right, so how do we find these absolute max and mins and local max and mins? First thing we need to do is define what we call a critical number for any function. A critical number, to find the critical number or numbers for a function, we take the derivative and we set it equal to 0, or we take the derivative and see where it does not exist, what elements are not, or what values are not in the domain of the derivative. So just to note, local maxes and mins always happen at critical numbers. If you think about it, the derivative is 0, it's going to be where the slope is 0, and that happens at the top of the hill and the bottom of valleys. Derivatives are undefined. Well, we saw that all sorts of funky things happen there. We could have asymptotes, we could have points, but if we're looking for local max and mins, the first key is to look for our critical numbers and then determine if they happen to be local maxes and mins. Be careful though, not all critical numbers results in local maxes and mins. We'll see that in a minute. So let's look at an example. We'll look at a pretty basic one. Let's look at the function find all critical numbers for f of x equals 2x squared minus 3x plus 1. So to find a critical number, we take the derivative. I got a cord crossing my lap right here. There we go, it should be better. Oops, sorry. I mean to make you motion sick. Maybe. Here we go. Let's look at the function 2x squared. No, it's supposed to just be f of x. There we go. Let's change that to f of x. F of x equals 2x squared minus 3x plus 1. We take the derivative. And we get 4x minus 3. We take the derivative and we set it equal to 0 or determine where it's undefined. It equals 0 when x is equal to 3/4. All right. It's never undefined because the derivative is a linear equation. The domain is all real numbers. So the only critical number, c equals 3/4, is the only critical number for f of x equals 2x squared minus 3x plus 1. All right, so now, if this function has a local max or min, it's going to occur at 3/4. All local maxes or mins happen at critical numbers. We can graph this in our grapher to save some time, put into x squared minus 3x plus 1. We know that this is a quadratic equation, opens upward, and it looks something like this. Okay, we can use the template for the vertex, the opposite of b over 2a. You can see that this is going to occur at 3/4, the vertex, right there. That would be our local minimum. So therefore, f of x has a local minimum at x equals 3/4. So this critical number is a local minimum. This has no local max. It doesn't make any tops of hills or any peaks going up. It goes straight up from there because we know how quadratic functions behave. So there's a local maximum at 3/4. Now I emphasize this because if I wanted to know the output here, I would put 3/4 back into the original problem. And if you put 3/4 back into this original problem, if I did my math correctly, it comes out to be -1/8. And this is important because sometimes the question says, where does the local max or min occur? Sometimes it asks what the value is. Anytime it asks for the value, it's asking for the output. So we would say it has a local minimum at 3/4. The minimum value is -1/8. So therefore, f of x has a local min at x equals 3/4. The minimum value is -1/8. So you just have to read the question carefully, see what it's asking for. All right, let's try another example. Let's find the critical numbers. For the function f of x equals x cubed. So simple polynomial. F of x equals x cubed, then the derivative is 3x squared. We set it equal to 0. X equals 0 is the only critical number. Usually we just call them c. You can say x equals 0, you can say the critical number is 0, but we can say c is equal to 0 is the only critical number for this function. So if x cubed has a local max or min, it's going to happen at 0. But if we graph this, we should know what a cubic function looks like. But if you forget, you can pop it into your grapher. It looks like this. So something kind of funky happens here at 0, but it's not the top of the hill or the top of the bottom of a valley. So c equals 0 is a critical number. But is neither a local max or min. So all local maxes and mins have to be critical numbers, but not all critical numbers are local maxes and mins. So just write that down. So what we get out of today, what we get out of this first lecture is all local max and local mins occur at critical numbers, but not all critical numbers produce a local max or min. So what we do, and I'll do some more difficult examples in a upcoming lecture video. So to determine local maxes and mins for a function, take the derivative, set it equal to 0, identify the critical numbers, And then also don't forget to check where the function's undefined. We did 2 polynomials here, so we didn't have any instances where the function was undefined, but we will come across those. Then you have to investigate. Look at those critical numbers. We can do it graphically. We'll do it using calculus shortly to determine if, in fact, those critical numbers are local maxes or mins. All right, so to keep my videos under, 15 minutes, I think I'm at 15 minutes right now, I'm going to end this and I will continue with a part 2. See you in a few.